And how will the other guys see this screen?
I haven't started broadcasting, that's why it's not showing up.
Oh, I have started.
Yeah. So,
Well, I started.
Like it's off.
yeah, I just wanted to make it go away.
You know, that's why I don't like it. It's indexing all the files, creating a lot of.
So,
How many started? How did you start it?
yeah, I started.
Okay.
Well, you're still like.
Sound works.
Do you want to go outside and see if you can still hear us?
It's almost there.
Okay, the video is here. Are you going to stand here and give the presentation, or do you want to go there?
No, I need to stay here.
This probably can be extended, and we can put this up on a table here.
Are you sure? I wouldn't like to.
How does it look though?
You wouldn't like to receive?
No, it was very hard to reach this point.
On the website?
We will just move the laptop. Just hold it.
Okay, that's fine.
There is also a USB with a remote mouse. So with this you can advance like CD, but there is a USB that needs to be plugged.
Don't worry. I can press
You can press
the key. But don't worry. That's not a problem.
Everything is set up here. It might not be better to grab some for you. You want to know or after the presentation?
2%. Yeah.
Yeah, don't.
Can we go back to the web
Yes.
browser real
This one. So I may right.
Click that link or click that tab. Make access. That one. Okay. Present to everyone. Okay, and now go back to your slides. Oh, it's a little slow.
It's slow.
Yeah, I see it now though.
Maybe with cable it would be faster, you know.
When I'm watching it on YouTube, it's slow. That's just because it's a lag airtime. Everything else is fine. I'm trying to figure out if I can go back and forth. I know how to do it. I figured it out. Because now it's on him. Yeah. So all I have to do is I present whichever one I want to show.
Okay, I figured it. It's all good.
Yeah.
Okay, thanks a lot. Well, but
It really started.
So you guys stay there? Yeah. Just,
Video seems to have a lot of lag. Almost a 3-minute lag.
First lab. And this weekend. Great. Just as excited. I won't be able to do that. But we'll be in Nebraska. So I'll be able to. I think we're.
Pay for washer dryer.
You are watching. I have the. Doesn't matter. Yeah, I can just do it all. We don't lose. Look at this. But you said you were more like. Depends on the server.
I try to be low. Right now, it's
There's no wonder.
My body was
still more or less about the time because I left my phone and my jacket. Yeah, but the problem is being aware of the time.
You're okay with analog time?
I'm perfectly
Okay.
Doesn't matter if they play on that stage. It's funny how Safe to say, I hear the same story.
Big announcement for students who are taking my AI course. All of you are going to sign in here. Both sessions. If you haven't already signed, please make sure you sign. There are two sheets here. One if you just add, everybody has to sign. Second sheet, which one? So this students in my course. Start.
Hello, while I was this girl, she was kind of
Oh, she tried.
little about her. My house, all the friends watching. Just like that. That's the question we went to ask. I like that. So she
Small screen on the side where you see the slide flow.
Okay. So, not yet caught. All right.
which I didn't track. So many things that happened.
Yeah, we started because outside.
Yeah,
Yes, like all the way to Southern Castles. Yeah, it's just like. I ran like one town.
Yeah, very
What was that? Always
oh, really?
just kind of like.
God bless.
Yeah, you just gotta. You said you know.
Posted about it.
Oh, did you?
There's like a student ticket for like $10, and I didn't see it, so I bought like the $150.
Oh, your seat was better.
Yeah, and then it has to be. There was this video about 45 minutes. And I was like, wow.
Yeah.
It's like if you
Let's start.
Okay. Okay, so let's start with the presentation. With introduction of our speaker today. This is Dr. Lino Marques. He is a faculty at ISR, which is the Institute for Systems and Robotics at University of Coimbra from Portugal. He, of course, has been leading the field research group there for several years now. He was extremely well known in the field, very well achieved researcher. He has several research papers as well in leading conferences and journals in his area. He also holds a BSc, MSc, and PhD degrees in electrical engineering from the University of Coimbra in Portugal. And he's a senior lecturer at the ECE department there, and also a senior researcher at IS&T. So I will hand him over to Lino now to give his talk.
Thank you, Professor Najluka, for the gentle introduction and for the invitation to be here today. And thank you, everybody, for attending to this talk. In a not so usual topic related with robotics. So we will talk about mobile robot olfaction. So we will talk about how to use smell in robots or by robots. The outline of my talk will be composed of those topics. First, we will have a brief introduction about mobile robot olfaction. Then we will look through animal olfaction. We will see several examples of animal using olfactory sense and how do they use that. Then we will briefly survey artificial olfactory systems, so basically gas sensors. Then we will look at olfaction in a single robot environment and multi-robot environments. But briefly, this will be the outline of what we will talk today. So why using, putting noses on robots? Well, first, it may be good to speak a bit about the sense of olfaction. On this, but we live in a chemical world. Everything is made of molecules. And in fact, all the animals are somehow chemical machines. Or can be seen as chemical machines. And if you know a bit of evolution and how life appeared and so on, it's not hard to accept that olfaction was the first sense that living organisms acquired. So first living organisms needed to sense their environment in chemical terms. They needed to get nutrients, so they needed to somehow move in the environment in order to be successful, so they needed to sense the environment chemicals. Olfaction, if you think a bit, right now we don't think very much about olfaction. We rely on vision. I mean, we humans. And if you see vision, I'm looking at you and I'm here capturing images from radiation that is being generated by each one of you. So vision, for example, is a sense that allows me to detect directly from distance. On the other hand, olfaction, I can only smell the molecules that enter into my nose. So olfaction is a local sense, but it's not so local because the molecules that come to my nose might have been transported by the winds. And so, in fact, the source of those molecules might be very, very far away. In fact, olfaction might be a more distant sense in that sense than vision. I might be smelling, for instance, smoke from a fire in a room that I'm not seeing here directly. Another aspect is that animals still use a lot of olfaction. If you look at some animals that that clearly everybody understands are using olfaction, like ants or dogs, or taking any animal that you know that that animal is using olfaction. Those animals usually, or some of those animals usually use olfaction to communicate among themselves. More or less everybody has already seen when an ant finds some food, it manages to somehow tell the other ants about the food, and the way that behavior or that process goes on relies a lot on chemical information. So animals rely a lot on chemical information. They use chemicals to send messages to other animals, although we might not be very aware of that, but it's everywhere. Even in mating, usually female generates some kind of pheromone from all species to the other animals from the same species in order to get together. So, and in fact, chemical communication is one of the least energetic, expensive process to communicate in animal world. Actually, we humans communicate a lot using voice, using sounds, but most animals don't use sounds to communicate. So a lot of communication is made sending chemical messages. Thinking about again, or focusing again about why using robots with olfaction. If we think about how humans use other animals to help them in terms of olfaction, everybody has passed in an airport and has seen dogs smelling and so on. So the fact is that our sense of smell is not so well developed nowadays because we evolved in a different direction. We don't rely so much on the sense of smell right now. But when we need advanced smelling capabilities, we frequently use other animals that can somehow help us. But using dogs, that's an example. For instance, that is an image from September 11, where dogs were used in very bad conditions. But it's quite common to see in any airport or any public facility using dogs to search for drugs, explosives, and so on. Or even, this is not so common, even using rats to sense mines, landmines in countries affected by those mines. So, thinking about some details about olfaction, something that probably some of you never heard are about pheromones. Pheromones are chemicals that are used by a species to send messages to individuals of the same species. There are sex pheromones, alarm pheromones, territorial marking pheromones, pheromones used for aggregation, and so on. So there are a lot of different types of pheromones. We can see some examples using pheromones. For instance, a female moth generates, releases some pheromones that are transported by the wind and eventually captured by a male that tries to follow the plume generated by the released pheromones in order to reach the female. This species, this silkworm moth species is a very well studied species in terms of mobile robotics olfaction and in terms of olfaction in general. In fact, the first pheromone to be synthesized was one from this silkworm moth in late 50s. And also the behavior of these moths, how do they manage to reach the female, is in terms of algorithmic aspects, has been a topic of intensive research during past years, because it is reported that male pheromone may detect a female at more than 1 kilometer away. If you think on the size of a moth, and so if you think on the quantity of molecules that are released, it's really impressive how it is possible to sense those molecules and track a plume until more than 1 kilometer. 1 kilometer, you use miles, that's okay. In fact, literature reports 1.4, so it's almost 1 mile. That's really impressive. So those silkworm moths have this shape, and they sense the pheromones using these antennas. Here we can see a close-up of these antennas, and it is claimed that the filaments of those antennas are able to sense even 1 molecule of pheromone. So if 1 molecule passes through, it can be detected, what is really, really impressive. There are no artificial systems that can do that right now. There are also a lot of animals that use olfaction to search for food. Actually, most animals use olfaction to search for food. What we can see here are images from a study done in Berkeley some years ago, where the behavior of a dog was tracked with LEDs. So there was here, I don't remember the name of this bird, but this bird was releasing a scent, and the dog was somehow tracking that scent. And what we can see here is that although the scent is transported in a more or less linear way, the dogs employ a strategy trying to track that sense, allowing for some robustness in terms of if the sense goes away. And what was done was comparing the behavior of a dog in this study with the behavior of a human person. So although we don't think on scents and on others, in that experiment, I think a vanilla scent track was laid on the ground, and a group of persons with their eyes covered were employed and were asked to try to track the scent. And what was impressive was that persons that are not trained exactly to track scents employed more or less similar strategies. So it's a strategy where the person or the animal looks for possibility of losing the track, and so kind of a differential tracking strategy in order to not lose the track. Another very well-known animal in terms of using behaviors, using chemical-related behaviors, are bacteria in general. In the 70s, a lot of studies were done with E. coli and other bacteria, and it was concluded that those bacteria could follow a chemical gradient using a very basic algorithm that was called biased random walk. And the idea of the algorithm was basically bacteria start the previous chemical concentration measured, does a move. If the move, after this move the chemical concentration increased, the next move will be more or less in the same direction. If it decreased, the bacteria provides what's called a tumble, so somehow goes randomly, but in the reverse direction. What can be proved is that this type of biased random walk somehow allows to follow gradients with this very basic algorithm that only requires one memory cell, let's say. So only requires storing the previous concentration value and knowing more or less the direction of motion, or at least knowing that I'm moving either in the prior direction or I'm moving in a different direction from the prior one. Okay, I'll try to move a bit faster. Another example of animal using scents are, for instance, bees. Bees, as you know, visit flowers or pollen. So in order to optimize this process, when a bee visits a flower, she marks the flower with the scent to know that that flower was recently visited. So as you know, scents evaporate, so in time they disappear. What happened using this process is if another bee visits that flower, it immediately detects that flower was recently visited, so goes away because that flower has no pollen. The mark released there disappeared with time, and when the mark has disappeared, the flower contains again pollen, and so that's kind of distributed optimization process that emerged from this use of others. Ants are well known to use scents for a lot of their tasks, including to mark trails and to optimize trails from a given origin to the target. Scents are also used, for instance, by territorial animals to mark the territory. That's also a way of distributed coordination among communities, in this case to manage competition among the animals of the same species. So if we, after this past number of examples, let's try to wrap up what we have seen and try to think about, in terms of robotics, what can we use scents for? And in fact, in summary, we can use scents either to go to a scent source or to avoid that source. Actually, there was a Greek philosopher that Plato that claimed that there are two types of scents: the attractive ones and the unattractive ones. And somehow, if we stick on that, we can think on using scents in robots, either to somehow manage, let the robots find a given source of the scent, or to avoid it. So in this case, we are imagining another source that releases hopefully an attractive scent, and the idea is the robot can sense that sense until the source. This can be useful, for instance, imagine that we are looking for explosives, a gas leak for something or whatever. That's the idea that we are targeting in this draw. We can use scents, for instance, to coordinate robots along trails. So instead of using localization and so on, we can just mark the trail and, for instance, if we have a patrolling task, so imagine that we want to patrol this building with a group of robots. If the robots somehow mark the places where they have been with a volatile scent, if another robot passes in a given area, like in the bees, the robot knows that that area was recently or not visited. So if it was not recently visited, that's a self-coordination mechanism that may be used to somehow have distributed patrolling without a centralized mechanism to coordinate that patrolling, or to transport things along That's another example. Or we can think in terms of repulsive smell. Imagine that we want to clean a large area, let's imagine an airport, using groups of robots. If the robots can smell the cleaned area by the chemicals released from the not so recently cleaned area, that's a mechanism again that can be used for an automatic coverage without any kind of localization and so on. So I'm assuming that everybody knows a bit about robotics. I don't know if you are aware that one of the problems in robotics is the robots usually need to self-localize. Basic problem in robotics is navigation problem, how to move from one point to another point. And so somehow those things try to, using smell, address those problems, but in a non-conventional way. Okay, to use robots, to use smell in robots in an effective way, we need to know deeply how others are transported, if we think in the atmosphere, by the atmosphere. Okay, basically, we can think in two mediums, either atmosphere or aquatic mediums. So let's focus, not complicate too much, just in atmosphere. So, and as you can see from this cigar releasing this smoke, as you can see, the mechanisms of other transport are not easy mechanisms. Smoke from the cigar, it's not a smooth plume. It's a very turbulent one that has some laminar regime here, and immediately starts bursting, and we'll have areas with very different concentrations. In fact, if we think on another patch, in a what's called low Reynolds environment, so something very viscous, the main phenomena of that happens with that concentration is spreading slowly, so in a diffusion only manner, and this would generate smooth gradients. But in an environment like in the atmosphere, that is not happening. What happens is that this is also happening, I mean molecular diffusion, but that's a very, very slow process, and in fact, what is relevant, it's what's called turbulent diffusion, where the patches are shred in pieces, like in the smoke of the cigar, and you came out with a very irregular structure that's called another plume. And in some places of that structure you can sense very high concentrations, similar to the one in the origin, in fact, and in other you can smell almost nothing. So, and this difficulty makes very hard dealing with odors and smells. If we think about we try to analyze what is called another plume. So another plume, the release of a chemical that is transported by the wind, let's call it a plume, another plume. If we look at the average of that phenomena, that average can be molded by what's called a Gaussian plume that provides this smooth pattern in terms of concentration. But I'm saying again that smooth concentration is an average. So imagine that you have a gas release or that you have a chimney that's releasing some chemicals. But what that represents is, for instance, half an hour average of what happened there, not instantaneous phenomena. If we try to look in a if we try to look in a scale, in a not so long-term scale, we'll obtain something like this. So imagine that you are above the plume and you are looking to the wall. What happens is that the wind generates that kind of fluctuation that represents better the plume, but doesn't represent everything yet. If we really want to go into detail, the inside of the plume is very, very complex, and this is bad, but it's also good. It's bad because the phenomenon is very complex. It's also good. I don't know if you guess why. Why do you think it's also good? I'll tell you. It has to do with that average, and has to do with why the male moth, is able to detect the female 1 kilometer away or so. The point is, due to turbulent diffusion, what happens is inside the every time smaller patches of odor, the concentration inside, it's more or less similar to the concentration at the release point. What happens is that we are shredding and shredding and shredding those patches. So this is good because if I can sense, for instance, here, I'll obtain a very high concentration, and so the probability of detecting that molecule is high, even far away. Is that because it's the resulting nature, it's almost chaotic, and so we have to deal with that. So the trick that we would like to explore is exploring concentration peaks instead of average, because this phenomenon on average may be almost zero, but the peaks might be, in fact it's reported that the peaks might be 3 orders of magnitude higher than average in other. So I'll go very, very fast on these artificial olfactory systems, since mostly computer science makes no sense to go into detail about technologies, but there are a lot of technologies to sense gases. The ones mostly used in robotics are the second one there, metal oxide gas sensors. Those metal oxide gas sensors are resistors that change the resistance in the presence of a given chemical. So let me, I don't go into details with this, but you are okay. I don't know if you have interest, please, let's try to not be a one-way talk. I'm happy to be interrupted, and let's try to interact if you need. Okay, so if you are curious about details of gas sensors, I can say a bit about that. Okay, one of the problems with the gas sensors is that they have several problems. One is that they are not so selective as the biological ones. I told you about pheromones and chemical messages. In fact, in biology, animals are very, very, very selective in terms of sensing. They know exactly that type of molecule, it's a pheromone from my species, so that's no doubt. In artificial systems, that usually doesn't happen. And what we have, most or almost all of those chemical sensing technologies that were reported or presented before are selective to a given chemical, but also to a lot of other chemicals more or less similar. And in order to manage that, or to increase selectivity, what we do is what's called an electronic nose. An electronic nose is a device composed by a set of different chemical sensors. Each one of the sensors is selective more to this and less to that. And the idea is combining the output from all of those basic sensors in order to be able to identify and classify the gas that is being sensed. So let's also pass. We did some work on this area. This is an example of 4 chemical sensors nostril. This is another more developed one, where the chemical sensors are embedded in these very tiny chips. This is about 10 years old. Right now we are developing things much smaller. This is an electronic nose adapted to a Kepler robot. I don't know if you know the Kepler. Kepler 2 was a very popular robot. Kepler 3 is not so popular. It's a bit bigger and it was very expensive. That's why it was not so popular. Very expensive for the robot. We did, as you can imagine, it's not only important to identify the smell. It's if we want to do something using smells on robots, what do you think it's also fundamental? Sorry?
To emit a smell?
The smell that's...
No, emit it.
To?
Emit.
Emit.
To give off a smell?
That is important, yes, to
Depending what you're doing.
for some but I mean about combining the sense of smell. In fact, if you want to, if I tell you, if you sense, let's say that you sense a smoke, how do you search for that smoke? Okay, smoke is visible. Maybe it's not a good example. Perfume, if you want to go.
If you have 2 noses, you're trying to locate the source.
That
right?
would be the obvious.
Exactly which one is getting.
That would be the obvious approach that I did long time ago, and it's not very good. But we'll go. We'll go for it. In fact, the most effective is knowing.
And that's why we have 2 molecules, right?
I'm not so sure about that. In fact, that's, maybe that's a question of. In fact, we are symmetrical.
Yeah.
We are symmetrical animals. We have we have 2 eyes, and we can benefit from the 2 eyes in terms of stereo and so on. From the 2 nostrils, I'm not sure that we can benefit in terms of stereo. In fact, probably I would go upwind. I would try to know where is the wind coming from and try to go, because I know that smell transported by the wind. So
at least we can say we smell on stereo.
we have 2 nostrils, but it might be just because we evolved as symmetrical animals, or you have it's more robust. If by some reason you have them, you lack one nostril, maybe the other one might be might be working. I don't know. But the fact is that using only the nose or exploring stereo from the nose, it's really, really hard if working at all. But the point is we realize that we need to combine also the sense of wind. We need to know where is the wind coming from and combine both types of information in order to have some kind of useful output. So some years ago we combined that type of both. This is what is called an electronic compass, so something that is able to classify others and know also where are the others coming from. So this is an experiment with a ventilator here with a cup with a volatile front of the ventilator, and we have a ventilator, white one, on the top of the lab, and we have the system in the middle. And this experiment consists in turning on one ventilator with a chemical, and that system identifying where was which chemical and direction, and switching off, switching on the other one, and being able basically to discriminate others and where they were coming from. So first we employed, this is a super scout robot with two nostrils, one here and the other there. That approach, that it works, but it's not in a realistic condition. It's very hard to obtain good results with this. Okay, this is an overview of the possible navigation tasks that we may explore. Let me just go through some tasks with that. There are several possible tasks that I already mentioned in fact, like searching for other sources, following chemical trails, mark areas, map an environment, and so on. And we can explore this with a single robot or in multi-robot environments. One of the reasons why I'm interested in using smell is also to explore coordination strategies. So multi-robot environments coordinated somehow by smell. So let's see something about other source localization. So if I want to to search for another source, basically we can say that I need to do three things. First one is detecting the chemical. If I'm looking for another source, let's suppose that I'm looking for fire in this building. First, I need to get some signs of smoke. So as far as there are no signs, I should keep looking at. So this is basically first task in this related with this mission, and the goal here is getting into contact with the molecules that we are looking for. The second, let's assume that in a given corridor I smelled some smoke. What I need to do is track that smoke scent until it serves. So that's the most obvious thing to do. And to do that, I need to do what is called plume tracking. And let's assume instead of smoke, that's a non-visible chemical, let's say benzene or propane. So that's a non-visible chemical that we can sense. So that gas that is used to cook, for instance, we can sense and it's not visible. So the last thing to do is identifying where is that coming from. Okay, as humans we can probably use some kind of reasoning with some vision. So if I see a gas tube, I try to inspect by different means and get from here. But if I assume that I have no vision or that I'm just using smell, I need to have some kind of strategy to find the smell, concluding that that is the smell source is being released from this point and not elsewhere. Okay, so in summary, we have these three tasks. So detecting chemical plume, tracking the chemical plume, by localizing its source. I can employ several strategies about localizing the source. For instance, this is a strategy employed a long time ago that's assuming that a gas source is coming from the ground. If I have sensors near ground level and on the top of a robot, we have a kind of a pattern that switches when the robot is far away, depending on the concentration of the chemical, on the molecular weight of the chemical. But assuming that it's a volatile that goes above the ground, the upper sensor is sensing higher concentrations than the lower one. When the robot passes near the source, that pattern reverses. That's a possible strategy. Right now, we use other strategies that are not here, but I can pass in a video, based on the estimation of the divergences. So if I can somehow estimate the divergency of the concentration, I can conclude that where a source can be. So some algorithms for plume tracking. Do you still remember the bacteria and the Weisbrand wall? So some years ago, I tried several of those algorithms and with the goal of trying to assess advantages and drawbacks from each one of those algorithms. So I tried bacteria, that was like a benchmarking algorithm, let's say the dummiest algorithm that we could implement on the robot. What seemed to be the cleverest algorithm, that was gradient following, so assuming two sensors on the robot, like that guy suggested, and let's try to track the gradient and reach the source. I implemented also an algorithm inspired by the moth while searching for a plume. By the way, that algorithm is more or less like that. When a moth detects some scent of interest, it goes upwind until eventually losing the detection. If after losing the detection, tries to capture the detection, starting a set of zigzags strategy. If those zigzag strategy fail, it loops back, trying to recover again the plume. So that's a state machine-based algorithm. And we did that with that experiment. I mean, we tried those three algorithms with that experiment with two other sources in an area where a lot of turbulence was generated, and with robots moving from here. And in fact, in summary, what we could conclude was that in that environment, most effective algorithm was in fact the one from the moth and not the gradient one. As in the beginning, I could expect. In the beginning, I was expecting the gradient to be the one performing better, but it was not. And after some years of work later, it was clear, because in fact the gradient there are no smooth gradients it's always jumping due to turbulence. So it's better to have a more robust strategy that somehow integrates the knowledge of the wind and so on than to assume that okay, I have to guess sensors, let me try to keep the same concentration and so follow a given gradient. We did also some work on 3D plume tracking, in this case with a robot equipped with a set of 4 gas sensors at different heights. And we did some mapping and some assessment on the performance of the different algorithms. In the past years, we have also expanded this type of algorithms to aquatic environments with a surface boat and an underwater platform. For instance, here of course, we knew where the pollution, where the output, where the other source was in this case, but this was interesting because it was a set of experiments in a river passing in Coimbra. where we could also, again, get confirmation that that type of state-based algorithms perform much better than any kind of gradient-inspired strategies. These some experiments related with exploration and odor mapping. But I will pass through since I have a video and the time is running out. Let me select what to show you. Okay, I'll stop a bit here in this slide because I think this is a bit related with some work that Professor Tupa is doing somehow. This was work where the aim was doing cooperation in between multi-agents, in this case a human cleaner and a robot cleaner. And the idea was to do online coverage of unknown areas, but this online coverage was somehow helped by the detection of scents. So what we have here is a robot that releases cleaning chemical, and so while it passes, leaves a trail, and has the ability, as a nose, to sense if an area, if a place was recently cleaned or not. And we have also a human cleaner that is also releasing that type of chemical. And the algorithm managed to coordinate automatically the robot independently of what of the areas that the human cleaner cleans. But this could be expanded to multi-robots because the coordination was in the chemical release and chemical sensing, and not on any kind of centralized approach that coordinates that. Okay, in terms of multi-robot systems, we have done a lot of work in terms of using multiple robots in emergency scenarios, and we did some. We tried to extract some knowledge about why using swarms or multi-robot systems and when, and try to identify advantages of using swarms related to how structured the environment is or not. I will jump just to the movie. I have a movie somehow summarizing this set of works. So let's. Ali was one of my PhD students that is now in EPFL in Switzerland. For instance, this work is about using a swarm of robots to detect other plumes. We have the other plume there in yellow, and there was a committee. We implemented swarming strategies that allowed, for instance, when a given agent detects the plume, to tell the neighboring agents that I'm in a good zone and neighboring agents were attracting. And so if that realized to be a good sign, it reinforces and allows the swarm to go much faster tracking the plume. Otherwise, it disappears and they keep exploring. And there were also some rules implemented in order to realize that the search was reaching. When the agents change color to blue, actually when they were black, they were searching for. When they were red, they were in the plume or detecting chemicals. And when they turn blue, it means that they reach the surface. This is about, yes.
Going on here, we are
If I have any, yeah, there were a set of, it was clear from the motion, yes. So this is about how to explore an environment in order to optimally detect another plume. So imagine that you are searching here in Nebraska, it's quite wide field, and you want to optimize the probability of detecting a given odor. So something is releasing an odor, you don't know where it is, you don't know where is the plume, how to distribute in the field in order to optimize the probability of getting into contact with that plume. That was what prior, I mean with a delay, my words are with a delay from the movie, I hope you can. Okay, this is a work about mapping using time series analysis. It was presented last cycle. This is taking some time long. And finally, this is work with 3 years old or so that is in structured environments like a large warehouse or whatever. How to explore that warehouse having with criteria also optimize the detection of a gas surge. So let's imagine that the warehouse has a fire. And so it's not a straight fire, it's in the beginning, it's releasing some smoke. How to explore that warehouse in order to optimize the time to reach the other source. So what we did here was to change the frontier exploration algorithm in order to take the chemical sensed chemicals sensed into account.
So in the search that you showed,
Yeah.
part of the robots were went through.
Yeah, while each robot, in this case it was not swarming approach, it was multi-robot approach, so there was topological mapping and so on.
So they have a map. So they have a map with them and
they don't have a prior map, they are building a map and sharing the topological.
Because I saw one robot that the left branch is exposed. So
that was mostly robots. And that's why in all of these studies somehow we try to extract some knowledge about why using swarms and where, and why using multi-robot systems where. So multi-robot in the sense of high processing and cognition ability. So contain maps and so on. Exchange more or less complex information.
Your sensors, how do they not get burned out? Because in the initial one, you discover a low concentration, but as they get towards the source, doesn't the concentration get so high, how can they differentiate those concentrations?
Well, if the concentration becomes so high, it saturates. That's no. Just saturates, so it means that you lose the ability of knowing that you are moving in a way that you will increase. But usually what happens is the reverse with artificial systems. Our problem is the ability of detecting very low concentrations. So what happens is that you only start detecting when you are already with a level. Those chemical sensors that we use, those metal oxide gas sensors, have sensitivities in the order of part per billion. Part per million is more representative about what. So it's good. It's very good if you compare, for instance, the type of gas concentrations that you expect detecting in a kitchen. If detect a potential failure, or in a mine, the guys that go into mines used to carry some sensors in order to know if the environment is becoming dangerous. So those sensors are sensing in the percentage or parts per milliard. So we are at least 3 orders of magnitude more sensitive. But for instance, if you want to sense mines, landmines, you need parts per trillion, you need 1 million better sensitivity. So,
And there's communication of spatial awareness of the swarm. So does the first swarm then tell the other swarms, I'm here? And it has to
you mean the agent swarm? It's the set of the swarm. It's the set of all robots. You mean one agent, one element of the swarm communicates with the others? Was that your question?
Yeah, so how is it self-actualized that's here and then tell all the other ones the coordinates are here?
So right now we the experiments that we do are in this type of environment. That's an environment with 4 meters by 3 meters, and with an overseeing camera and all the infrastructure that allows us to, for instance, not use the real range of communication, but by software saying that, okay, your range of communication is, let's say, 1 meter, so only those agents are allowed to know that you sent that message, for instance. In a real environment, the physical constraints will...
So this one right here, so the agent that's coming closer to...
So that if you look, the one that will get into contact, that's the one, that one will tell something to the others, and the message is spread somehow. Hopefully, the idea is spreading to the neighboring agents, although I don't know what was the radius considered in that case in particular.
So is the routing software something you have to program in the program?
Sorry?
The routing software allows you to...
route data to send.
No. Usually we don't need to do that. So because we are not working we are not dealing with the communication. Our deal with the communication is constraining what already exists, not developing new protocols, or I don't know if you got so. So the constraints imposed are imposed by us because we want to try a given aspect of the swarming approach, and we are not interested in exploring different communication protocols that are more or less adapted to that type of usage.
I think we'll let you get done with the talk first, and then we'll take other questions.
My question is about how to get the...
After the talk, let's do talk. Because we are on one talk, we'll just let you finish the talk, and then we'll take questions, and then we'll talk.
Okay.
So you have some more slides to go through, right?
No, I do, but I was assuming that that's why I had, but I was assuming that it was okay too.
Yeah. If you're at the end, then it's fine. Then we can.
Yeah, I think it doesn't make much sense to go into those lot of details and for all of this audience.
You have some end comments to wrap up your talk to saying what the take home for us should be, and then we can open up for questions.
Okay. Well, to wrap up, I would say that this is this is a topic not very much explored topic that I would say that I see myself working on this in several years to come. I'm particularly interested in researching swarming aspects using chemical communication, and what we did is very few. When I mean chemical communication, I don't mean communicating by radio frequency with neighboring robots. That's what we have done. I mean using really chemical marking to communicate with other robots. That's what, even in terms of hardware, that's challenging, like developing ants or robot ants to do something. That's one of my goals in the near future. That's exactly developing small robots with all the abilities. I passed through very fast. Sometimes we do some kind of adaptations to either existing robots. For instance, this camera contained a nostril here, the vacuum tank, and contained also, not this one, but we had another one that contained also the ability to track its way. But that's ugly. What I aim to do is something really adaptive to research on this field. So a robot really able to deploy different chemicals and to sense different chemicals, something very great and not something bad.
Okay. Let's thank the speaker first.
My question is about having different chemicals, because this is seems to be the practical for one smell that's used.
Most is for one smell, not all. For instance, that's
What happens when you have millions of smells, and how do you implement that, and how do you...
millions right now. You should forget, because but some smells, for instance, this work. Okay, this was for two smells, for instance, that is other compass, but this robot was used here. This was also with two smells, methanol and ethanol, but mostly we try to use chemicals harmless to the humans, can use on the lab. And usually, okay, those metal oxide gas sensors have a property. They only detect chemical volatiles that oxidize, so that react with oxygen. Seems a limitation. It's not so big limitation, because in fact, almost, for instance, I wouldn't say all, but almost all probably to be on the safe side. Smells that we can smell are molecules that oxidize. So the number of things that oxidize is huge. So it's not a so big limitation. But we try to use mostly harmless volatiles. And if we are, for instance, interested in researching a plume tracking strategy, you don't need different chemicals. You are just interested in how to manage the plume. So you need to sense, and your algorithm needs above all to manage the plume.
So, like, I was thinking during your talk about the benefits of like odors for like range detection of like source. So since they broadcast, like there's plume that goes out over a certain distance. Because right now I've seen a lot of your sources are like within 2x5 meter areas or like 4x5
mostly you're right.
But how, like, what are your thoughts on the future of odors as like detecting long range?
Well, first, it's not. For instance, here this is the hall of my department, and this is huge. In fact, starts here, maybe 200 meters long. You cannot see it all on the picture, and a lot of meters high.
So
but that's an interior environment anyway.
So it'd be more like a local area, as opposed to like we can detect infrared, like infrared marked things. We can shoot infrared light at it. It'll transmit to us, hey, this is the location that we've got miles away. So this is more like a localized area. It's just like
Well, the reason for so far having worked mostly indoors, it's because indoors it's more convenient. You can have a controlled environment and so on. But in fact, one of my, I would say, in this area, I have two main research goals right now. One is going outdoors, and we are working on that. And another one is exploring the swarming aspects deeply or more in deeper detail using olfaction. So going to outdoor robotics, that's not so far future, I would say. That's planned. In fact, one of the PhD topic of Gonçalo, that was one of the guys involved in the competition, is exactly that. But he has been working on other things last night, so it's on hold right now. But yeah.
Does the chemical makeup of some scents make it harder to try to detect, or is it pretty easy to, like, here is a scent, look for this one, and then they can sense it?
If you buy an electronic nose, you do probably something like what you are saying. Since we built our sensors, so we already built sensors to detect some given chemicals that we aim to use. So,
but does it have trouble picking up some scents more than others, or is it all pretty?
Yeah, sure. That's why given sensor is optimized, let's say, for ethanol. Alcohol. It doesn't mean that it cannot detect, for instance, I think it's ether. I don't know if ether. Basically, any solvent can be detected, but what happens is that specific sensor is better for ethanol than for the others. So if you use the others, you will get some detection, but not so good.
So then if that's the case, how do you?
And that's why what you need to build an electronic nose. Let's say you use one for alcohol, one for gas, one for.
That's why it's swarming.
We are not using the swarm on that aspect. And in fact, long time ago, I did a work called spread nose, where the idea was more or less that. So having different elements tuned for different things and explore the multiplicity of the sensing capabilities in swarm to come out with classification abilities.
I have a quick question to ask about the single robot wing tracking. In the algorithm that you have, like the moth's flying behavior or the radiant descent algorithm that you talked about, do you have any issue about the search getting stuck at a local optimum?
It depends on your environment.
Exactly. Like in the scenario that you showed, there was an odor source and there were pink blue coming out and you had an obstacle, an L-shaped obstacle.
Oh, that was wrong. That was not.
That was just an example.
That was just an example. If you do something like that, might be
local.
Might be a problem.
Yeah. Along those lines, do you use fluids, physics to try to predict, like in the water scenario, does your robots know that plume and river system is probably going to take this shape, so you need to start searching in that manner?
Yeah, and those slides that I didn't present, in fact, take that into account. So you know what's the average of the plume, so you know how the shape statistically should be, and so it means that if you want to obtain the probability of detection for a gas searcher, you should have that into account, and you should have that into account, and in order to optimize. So those papers about optimizing coverage or plume detection and so on take that physics into account.
Any more questions? I have one more. I was just curious. Is this pretty much all ground-based robots at this point? Or
Yeah, it's pretty much ground-based robots fine. Although there are some works on water as well.
I was more introduced. I was more on the last like drones.
Actually, the outdoor work aims to use a ground-based robot with a volume. So, drone. There are some works using drones to find gas sources and so on. The problem with that is, okay, if you are looking for a huge gas source, let's say those places where you put garbage. No, yeah, if you are looking for methane coming out from the land, that's fine. You have a small drone and you have a 1 square kilometer or so land, so you have a huge source, no problem. But if you are looking for a small, let's say that this is a gas bottle and it's leaking, so the propellers of the drone will mix everything, so it makes so much sense to use a drone for going for fine detail.
Okay, let's thank our speaker once again.